we learned how to find the area between two curves, and the general idea behind that is just to do the set up a definite integral from a to b of the top function minus the bottom function, whichever one is on top minus the bottom. So hopefully you did okay with that. There's one extra little challenge sometimes, especially with the calculator problems, sometimes even with the non-calculator problems, where you have to figure out what those boundaries are. Without a calculator, you just set the equations equal to each other and solve for x. You do basically the same thing with the calculator, except you're going to be looking at the graph and figuring out where that point of intersection is. So today we're going to start talking about volume instead of area. So we're going to sort of level this up into the third dimension. All right, so let's say we've got a caret that's 10.5 centimeters long, like in the diagram. Now let's say the question is, what's the volume of the caret? We'll ignore the leaves on there, just the caret itself. One way that we could approach trying to find this volume is to chop up the caret into small cross sections. Now if we chop up that caret and we end up with pieces like this, and I'm not really much of an artist here, so bear with me, but more or less, you're going to have pieces that look like this. Something like that. A little leaf on the end, right? Now, if I cut it up, approximately, or just kind of roughly, what shape are each one of those pieces? Rectangle. Well, they're three-dimensional, right? So let's start with that. Cylinder. Yeah. This is roughly a cylinder. Right? We've got a base that's approximately circular. And we've got this consistent, what you would call the height back in geometry, which is the distance between the bases. Right? So we've got a cylinder here, a bunch of little cylinders. And what we could do is find the volume of each one of those cylinders separately and then add them together. Right? We do know the formula, or hopefully we do know the formula for the volume of a cylinder. It's the same thing as the formula for volume of a prism, which is the base area times the distance between the bases. Usually call that height. Although, since it's not going to be vertical here, height might be a little misleading. It's just the distance between the bases. So when you have a cylinder, okay, you've got a radius, right? Call that R. You've got this base area, which you'll find given the radius. And you've got the height, which I really hesitate to call it the height, but it's the distance between the bases. Okay, I'm going to call it height just because that's sort of take you back to your good old geometry days. You would have called this the height, right? So the formula for finding the volume of a cylinder, and this is not something that would be given to you. You need to know this, is the base area, which I'll just call capital A for area, times what I'll call the height, although we're really thinking distance between the bases. Now, the formula for area of a circle is pi r squared, right? We know that, pi r squared. And that's basically how you find the volume of a cylinder. Now, one thing I want to just throw out there, something to think about that's not really related to what we're doing today, but just to kind of throw it out there as just like a separate little something for you to think about, is we know the formula for area of a circle, right? It's pi r squared. What do we get if we differentiate that with respect to the radius? So if you have an equation pi r squared, just a quadratic, pi is a constant, differentiate that with respect to r, what do we get? Not integrate. We're finding antiderivative, just differentiating, going the other way. 2 pi r. Now that formula should look a little familiar. And it's not coincidence here that here's the area of a circle. Here's the circumference. Just something to kind of think about here. And maybe you might think about how these formulas might be related to the volume of a sphere formula. What is the formula for volume of a sphere? Anyone remember that one? 4/3 pi r cubed. I want you to think about how you might get to that. Is it 4/3 or 1/3? 1/3? 1/3 pi r cubed? Either way, think about how you get there from those two formulas. Okay, just some food for thought there. Let's go back to our business here. Just a little separate note there. Okay, so we've got these little cylinders, or instead of calling them cylinders, because these are going to be pretty narrow, I'm going to call them discs. Yeah, discs. Let's say this chart below gives you the area of each cross section. Now, the area here is not going to be computed by pi r squared, because if you have a real caret, the cross section isn't going to be perfectly circular, right? We're just trying to get an idea of roughly what it would be. But these values are going to give you the actual area. So it says, use a left Riemann sum with 7 subintervals of equal length to estimate the volume of the caret. Basically, all we're going to do is calculate the volume of each individual disk or each individual cylinder and add them up. Now, as far as which area to use for each individual one, since it's asking for a left Riemann sum, we'll use the left area. So like for this first interval, we'll use 0.4 as the area. And the height, or the distance between the bases, would be 1.5 centimeters. All right, so let's set this up. We've got a total of 7 subintervals. Each one is of equal length. So we're basically, these cross sections will each have the same distance between the bases, 1.5 centimeters. And so we could write this out as, the base area 0.4 times the height 1.5 plus 0.43 times 1.5, so on and so on. And we only have 7 intervals here. We're not going to include the 0.9, right? Because we're going to use these 7. We're going to use the left partition to determine the area. So plus 0.48 times 1.5 plus 0.52 plus 0.56 plus 0.62 plus 0.72. All these times 1.5. Now, this can get a little tedious to write it all out, but when you have intervals that have equal length, you can factor out that 1.5 factor from each term. You can write it a little simpler like this. 1.5 times 0.4 plus 0.43, et cetera, et cetera. So just a little bit of an easier way to write this. It takes, not as much effort here. Now, we're not going to compute this by hand. Normally, we'd bring up Desmos, type it in, or whatever calculator you're using, and get your answer here. But I'll just save us a little bit of time and give it to you, because I don't want to waste time typing all that in. 5.595 cubic inches. So this is an estimate for the volume of the given caret. Any questions so far? It's been a little while since we talked about Riemann sums. Okay, so that is an estimate, right? We chopped the caret into 7 cross sections, and we measured on like the left-hand side what that area is, and used that to estimate the area of each the whole thing, right? Of each cross section within the cross sections. So, but how could we get a more accurate value here? What do you think we could do differently? Just in general, I don't need any numbers or anything, but just conceptually, how could we get a more accurate volume here? Yeah, use smaller intervals. Exactly. The smaller you make those intervals, the more accurate these areas are going to be for the little discs, right? Because on any given cross section of this caret, you might have something that does something like this, where it's like not a perfect cylinder. But if we make these smaller, we'll get like closer to the actual value. It's kind of like when we originally learned about Riemann sums and how they could be used to find the area under a curve, right? When we have a curve, we draw these rectangles, we can get a better estimate if we make those rectangles smaller for the area under the curve. Same kind of idea. So to get a more accurate approximation, we want to have more cross sections. Okay, the more cross sections you have, the more accurate your estimate will be. In other words, you want to have smaller intervals. More pieces. Now, if we wanted to have like the perfect value, like in other words, the exact volume, if we want the exact volume, what we would want is for these cross sections to be as narrow as possible. In other words, they would have an infinitesimally small interval length. Not quite 0, but a little bit more than 0. Yeah, as small as you could possibly get. In other words, we'd want infinitely many cross sections where the interval length approaches 0. So we'd have these real skinny little discs, and we find the volume of each one and add them all up. All right, so if we have a formula for the area of the cross section, say, okay, we know it's not actually circular. It's going to, be some kind of irregular shape here. But we do have a formula here given that will give us the area of any cross section X centimeters away from like the left-hand side. We can use that to find the total volume. So let's sketch a little diagram here so we kind of understand what we're saying here. So I'm going to sketch out my little caret here. This isn't really an art class, but do the best you can. Here's my little caret. My little leaf on there. Okay. The length of this caret is 10.5 centimeters. So I'm going to label this as 10.5 right here. And what we're going to do is we're going to slice this up into small cross sections. So like for instance, here's what one of the cross sections might look like. Like let's say I cut it right here. Now, this is going to be like a 3-dimensional diagram here. So when you draw that cross section, it'll look something like this. So like a little disc. Now, we need the base area and we need the quote-unquote height, but really the distance between the bases. These are two values that will let us calculate the volume. So let's start with the base area. The base area, even though it kind of looks circular, we know it's not exactly circular. We're going to use that function a to give us that area. In other words, like this base, that area the base area is given by that function, that a of x. But what about the height, quote unquote height, or the distance between the bases? What is this? We want that to be like effectively zero, right? We don't want it to be zero, but it needs to be like pretty close to zero. So we want a unit of infinitesimally small distance in the x direction. And that is what dx is. Dx is that infinitesimally small unit in the direction of x. So if we want just the volume of this one little disk, it's the base area times the height. Right? The base area, A, times the distance between the bases, which is dx. Now, that little formula will give us the volume for one of these, but we want all of these little disks all throughout the caret. So, you've got another one over here. We've got another one going over here. Right? We got a lot of these disks. There's infinitely many of them. We want to add them all up. All of these disks are going to be in between 0 and 10.5. So to sum up all the disks between 0 and 10.5, we can set up a definite integral just like this. And so what this will do is give you the total volume. Now, this would be something that you would throw in the calculator. So I'm not gonna waste time with that. But you just type in the equation with the integral, and you should get your total volume, which is 6.020 cubic inches. Any questions so far? All right, let's take a look at another one. It says, consider the graph of y equals sine of x squared plus 2 on the interval 0 to 3. First question is just simply asking for the area under the curve. This is old stuff, y'all. We know how to do this. The integral from 0 to 3 of sine of x squared plus 2, all that times dx. You just set up a definite integral. This is not something you'll be able to do by hand. We don't know how to find the antiderivative of that. That's not something you'd be expected to do. Might try a u substitution, but it's not going to work. So you just put it in your calculator. All right. We're going to skip the calculations here for time. 6.773. So this is kind of old stuff. I think you'll have a better appreciation for this if you follow along. Okay, so part B. This is where it gets three-dimensional here. It says find the volume of the solid created when the shaded area is revolved around the x-axis. So we're going to take that region and rotate it. This is something that's kind of hard to visualize. Okay, so what I've got here is that this top section is like the cross section, or not the cross section, but the region rather. We're going to take this region and revolve it around the x-axis. So it's going to kind of look like this. Okay, imagine you have like a cylinder, like a soda can, that's kind of like been, abused, like kind of crinkled in a little bit. Okay, kind of crunch it a little bit. And then, okay, now it's not really a cylinder anymore, yeah? That's kind of what it looks like. Let me show you, though, more precisely what it looks like. Okay, I've got this demo linked on our website that you can find. Just right on here, it says interactive demo. You can click on that, it'll bring you to this. I've already typed in the equation that we're looking at here. But so this is the region we're dealing with, and we want to revolve it around the x-axis. So I want to just kind of show you what that really looks like. I'm going to rotate this xy plane in the third, and rotate all the way. So there's the back end. Here's the front. This is what it looks like when you look at it dead on, right? As we rotate that region, can I grab this? It's not gonna let me do that. There we go. All right, so it's going to rotate. It's going to go around. Let me just stop there. So you can kind of see, I haven't gone the full way yet, but you see how it's rotating around? Okay, and now I'm going to take it all the way. You get this kind of vase-looking object. All right. So this is the object that we're trying to find the volume of. All right, let's go back. Okay, so we want to find that volume. And we're going to use something called the disk method, because what we're going to do is essentially like chop this up into little disks. And here's how the disk method works. Well, you kind of already know, right? Basically, we're going to find the volume of each individual disk using that cylinder formula, and then add them up. No big deal, right? Conceptually, it'll look like this. The integral from 0 to 3 of the base area times the, not the height, but the distance between the bases. We've got the base area times the distance between the bases, dx. So this is where you really got to focus here. The base area is a circle, right? The area of a circle is pi r squared. So if I want to break it down a little bit more, I could write it like this. But r is not defined anywhere here. We need to state clearly what is the radius of each circle. Now, if I go back to this demo and I drag that disk, you can, let me kind of pull it back here, just so you can kind of see it in 3D. As I move this disk, you can see that the radius of the circle changes, right? Each one's different. And that depends on what the x value is, right? So you got a real tiny one there, and then you got some bigger ones out over here. The radius changes as x changes. But the radius is really just this distance from the x-axis to the value of the function. All right, it's this distance right here. From here, well, let me get a different color here so you can see it. It's like from here to here. Here's our radius. And the radius is different, right, for each individual piece. But that radius will always be equal to the value of the function itself. Right? This radius here is equal to the value of the function when x is 0, when x is whatever, when it's different for each one. But we can calculate that using the function that's given. In other words, the radius is the sine x squared plus 2. So this is how you'd actually type it into Desmos. Pi times the radius squared dx, where the radius is sine of x squared plus 2. Now, we've got everything in terms of x now, so there's really no simplifying that you need to do. We're just going to type that into Desmos and get an answer out of that. And we get 51.536 cubic units. There's no units given here, so we'll just leave it at that. Any questions about that one? Exactly. You're basically like chopping it up into little circles, finding the area of each circle, and adding them all together. That's basically what you're doing. Y'all see that? Just like chopping this up into effectively like sheets of paper. And each sheet is a circular piece. You're finding the area of each one and adding them all up. All right, should we make this a little bit more challenging? Oh, yeah. Because you might not be revolving around the x-axis. Like in this problem that we just did, what I'll call the axis of revolution was the x-axis. Right? But what if the axis of revolution was something else? Like what if it was y equals -1 instead? So I want you to like just try to picture what this solid would look like in your head. Kind of sketch it out. So like here's the x-axis right here. Here's y. This is -1 right here. Here's 0, you know. So I'm going to take that region up top and revolve it around y equals -1. When I do that, I'm going to get something like this. All right, it kind of looks like a toilet paper roll if like the toilet paper has been like manhandled. Like, you know, I've got little kids at home. And I don't know what they do to those toilet paper rolls, but it looks all mangled like this. I don't know what they're doing. It's like manhandling it. Yeah, but what's going on in the middle here? You've got a hole through the solid. This is like the cardboard toilet paper roll holder, right? The thing that it's all wrapped around. Well, let me show you a 3D version of this. Yeah, like let's say if we want to go around -1 here, it's going to look like this. Okay, see how it's kind of a very similar object here, but it's got that hole right down the middle. Okay, so as far as how we're going to compute this volume, it's going to be kind of similar to the area between two curves idea, where we have like the top curve minus the bottom curve. Okay, we're going to find essentially the area of this big circle and subtract away the area of the small circle. So let's write down our sort of the idea here. From 0 to 3, we're going to have the big circle, the area of the big one, minus the area of the small one. And then multiply that by dx. Now, because the shape that we're adding up over and over again is not really a disk, this is called the washer method, or like a washer problem. Now, I don't mean like a clothes washer, a dishwasher, anything like that. I mean like a washer, like a tool, the washer that looks like this. You know, something like if you ever built something with screws and nails or something you put between the screw and the nut. Yeah. So that's the shape that each one of these things are going to be. Kind of hard to sketch it all the way in there, but something like that, you know. Okay, so we got to have the idea here, like the concept down. But we really got to make sure that we're coming up with these areas correctly. And the big challenge here is making sure that your radius is correct. So I'm going to try to go slow here. Okay, the integral from 0 to 3. Okay, so the area of the big circle. The big circle has a radius that goes from here to here. So maybe I'll call that capital R for big radius. And then the little radius goes from here to here. I'll call that little r. So this is going to be pi times big R squared minus pi times little r squared. Now, the little r, I think, is going to be a little easier to come up with because that we've got like a horizontal line there. It's a constant radius, right? This distance from here to here doesn't change all throughout the solid. It's just, what is that radius there? Yeah, it's just 1, right? So this is 1. But what about the other radius? The other radius is the height of the function, but plus 1, because it's like 1 above what we're revolving around. So this is the value of the function from 0 to whatever, plus this 1 unit here. So in other words, like this is y plus 1. Okay, so let's see if we can write this out. So we've got pi times the big radius, which is sine of x squared plus 2, and then plus 1 squared minus pi times 1 squared. And all that, maybe I'll turn these into brackets just to make it a little easier to read, dx. Now, it might be nice to come up with like a sort of a generic way to come up with this radius, right? So that's what I'm going to write down next. Is like if the axis of revolution is below the region, then the radius will be the function minus the axis of revolution. So like in this case, it's the function, I know it looks like plus 1, but that's because it's actually minus negative 1. A little shortcut to get there. And the same thing's true for like your lower boundary here. Right? This is just y equals 0. 0 minus negative 1 is positive 1. So that gives you that radius also. Now, we've got the whole equation put in there now, so we can throw that into the calculator and get about 94.096. But typing that in is kind of the least interesting part of the whole thing. Who cares what the answer is? Any questions about that one? All right. So this is an example where that axis of revolution is below the region, but what if it's above the region? What if we got to revolve like upwards rather than downwards? Let's get a little different here. So let's say we want to revolve that region, which is actually this lower region down here, this one. I can't really see that, but this one right here, that's the region. Let's say we want to revolve it around the line y equals 4. So here's 4. That would mean like here's 8. Yeah. So if I'm revolving that region around y equals 4, this point right here gets revolved around, does something like this. Yeah, the point down here revolves and you get something like this. Oh, let's try that again. Don't really see the inside there, but we have another like roll of toilet paper here. But this time, it's the outside function, or this the large radius, which is constant, right? But the inside tube is all mangled up, yeah, and defined in terms of the function. So it kind of swaps how we're going to reference the big radius versus the small radius. Here, the big radius, well, the big radius is pretty obvious here. What's the big radius? 4, right? From here to here. Big radius is 4. The little radius, now this is something that's a little tougher to come up with. So let's think about how we might get that. Let me zoom in on here. All right, so the radius is the distance between the axis of symmetry and the function, right? So for instance, like we're looking for this as like the little radius here, right? Now we know the distance between 0 and that function is the function itself. Like from here, let me try a different color here. From here to here, can you see that okay? That is your sine of x squared plus 2. Right. What's the distance between the x-axis and the axis of revolution? 4, right? Meaning like the distance from, running out of colors here, from like here to here is 4. Let's put that maybe over here. So if we know that this height is 4, and let's say that this height was like 3 right here, just throwing out a number. If this is 4 and this is 3, what's this leftover distance? Yeah, or in the case of the example I gave, if this is 4 and this is 3, what would it be? 1, right? Yeah, so it's going to be 4 minus that function value. Or in general, it'll be the axis of revolution minus the function value itself. So I'm going to write down basically a similar statement here and say if the axis of revolution is above the region, then the radius is the axis of revolution minus the function. So let's see if we can set this up. Same setup as the last one here. We've got an integral from 0 to 3 of the big circle, the area of the big circle, minus the area of the small circle, dx. Okay, the big circle, well, actually both of them will be in terms of pi r squared. So let's just go ahead and throw that in there. So we've got pi times something squared minus pi times something else squared. All that times dx. So going back to the radii here, the large radius from here to here is 4. And the small radius is that 4 minus the function. It's that leftover distance. So 4 minus the, am I going to squeeze that in there? I'm going to have to write kind of small here. 4 minus sine of x squared plus 2. Now again, once you got that set up, just throw it into Desmos, you'll get your answer. Okay, we should get here 118.701. Any questions so far? All right, we got time for one more example here. Let's at least get the next one started off. We probably won't finish it, but that's okay. We'll come back to this next time. But at least just to give you like one more to chew on here. Let's try this one. Well, we'll see how long. We've got a little, what, like 10 minutes? Yeah. Okay, so let's say, this is an old AP problem. It says let R be the shaded region in the first quadrant enclosed by these two functions in the y-axis as shown below. First, find the area of that region. So this is going to be old stuff here. We're going to find the integral from 0 to wherever this point of intersection is. Or we might need to figure out what that is. So let's type that in. Y equals e to the power of negative x squared. And y equals, let's see, what was it? Cosine, 1 minus cosine x. And so, yeah, that point of intersection is not quite at 1. It's at 0.941. So that's going to be my upper bound. Okay. And then to find the area between two curves, just do the top minus the bottom. Now, what I would recommend you do, especially on the AP test, but especially also when you're just using Desmos, you don't want to have to keep typing these functions in over and over again. So give them each a name. Let f of x be e to the negative x squared, and let g of x be 1 minus cosine x. And then when you do it this way, you won't have to rewrite those expressions over and over again. And so instead of writing like e to the negative x squared minus 1 minus cosine x, making sure your parentheses are all good and all that, you can just now say f of x minus g of x dx. Now here's f, here's g. It's just a little bit easier way of setting it up. All right, and that's something you could also just type into Desmos. So we got 0.590. Okay, so that's old stuff. Let's try to revolve it around the x-axis. Okay, so we're going to take that region and spin it around the x-axis. A little hard to sketch here. We'll do the best we can, but it's going to do something like this. And then you're going to have a little, basically like a hole here. You've got this, it almost looks like a cone shaped hole in this object, where the point is right on the edge there. Okay, so if I were to take a single cross section, just to kind of give you a better idea of what each cross section is going to be like from here to here. All right, you've got this little hole inside. Kind of hard to, that's not really the best. Maybe I should bring out, that looks pretty messy. It's really hard to draw these, but let me pull it up on here. It'll be a little bit more obvious. So we've got e to the negative x squared, the inner radius being 1 minus cosine x. And we're going from 0 to 0.941. Okay. Oh, and we want to be going around the x-axis, don't we? There you go. All right, so here's what it looks like. Okay, you can see it's got that cone-shaped hole in it that you can see through, but on this side it's totally solid. Okay, so that's basically what we're working with here. And so technically this is going to be a washer-style problem. So we're at from 0 to 0.941. The area of the big minus the area of the small, dx. Okay, so it's going to be pi r squared minus pi r squared, where the large R, here's the big R, is going to be defined by that top function, and little r will be defined by the lower function. They're both going to be variable here. So we have pi times r squared minus pi times r squared dx, where the radii are defined by each of the two functions. So we've got the top is f, and the bottom is g. If you've got this all typed into Desmos, you will get your answer here, which is 1.746. All right, I think this is probably a good place to stop today. I'm going to give you your homework, and next time we'll do some more with this. Okay, we're not quite done with volume. We have one more day of volume.